Forgot to make this morning, the U.S. Marshals Service is on site. They are wearing white lapel pins and will be here throughout the program, and they will be throughout the resort. If you have any questions or safety concerns, please contact an LEC staff member or one of the marshals with those concerns. All right, well, thank you very much for coming back, and thank you for being here for our symposium on scientific methodology and the admissibility of expert testimony. We are moving to our second lecture, The Nature of Expert Evidence and the Incomplete Nature of Science. As you will note in this program, we have a series of lectures that build on each other, hoping that the overall understanding of the scientific method and scientific methodology and expert admissibility will then move to practical applications in your courtroom, some case studies later in the program as well. So it's a very nicely built program that will cover a lot of areas that will be useful to all of you. And we are delighted to have Professor Gary Marchant here, who is a Regents Professor of Law and Director of the Center for Law, Science, and Innovation at Arizona State University's Sandra Day O'Connor School of Law. He received his JD from Harvard Law School, where he received the Fay Diploma, which is awarded to the top graduating student at Harvard Law School. And among his other activities, Professor Marchant has served for the National Academy of Sciences 5 times on 5 committees, and has been the principal investigator on several major grants and organized numerous academic conferences on law and science issues. Truly an expert in the field. You can read more about his bio and all of our speakers' bios in the written materials that you have at your desk. I hope you will take a look at his overall expertise and other credentials, but so that we can get the program going and learn, I'll keep it short and turn it over to Gary.
Great. Thanks, Don, and I'm delighted to be here. A very exciting conference. So many of the things I wanted to talk about are going to actually be talked about in later sessions, so I apologize to future speakers if I steal any of your thunder. I try to tread lightly and superficially on your topics, and so you'll be able to go in much more detail. The topic I was given was nature of expert evidence and incomplete nature of science. So I didn't pick that. I think it's a fascinating topic. I'm hopefully interpreting it consistent with what the organizers intended, but basically, science is incomplete. You've got a sense of that from the previous talk. But it's asymmetrically incomplete in a way when we talk about risk, which is sort of an area I'm interested in. It's easy to prove something is unsafe, is dangerous, or actually, to be more correct after Professor Johnson's speak, it's easier to disprove or refute or falsify that it's safe. You can't prove the absence of risk. But what you can do is you can create what's called the null hypothesis, that this does not harm you, and you can falsify that. And that has been falsified for a number of different things we get exposed to, things like tobacco and benzene and asbestos and radiation. And those have been repeatedly falsified, the null hypothesis that they're safe. And so we can be pretty sure that those are dangerous. We can put them in that box, and we should live our life that way and try to avoid getting exposed to those bad things or minimize our exposure, and we can be pretty sure about that. Now, nothing's certain for sure. I just recently read an article that the whole world's a simulation, and they actually quoted a guy at Oxford, Nick Bostrom, to say there's a 21% chance the whole world's a simulation. I don't know how they get that number. I can't imagine that's an exact number, but the idea is that there's some supernatural thing up there who's sort of just manipulating us and trying out different things. And so they'll say, push a button, COVID for a year, see how these people do with that. So we may be living in a simulation. It's not really, nothing's real. But I don't think we can live our lives that way. So let's assume that's not the case. So in the real world we are living in then, we can put things in a box and say they're dangerous. But the problem is, and why I think science is incomplete, is we can't put them in a box and say they're safe. How could we show something is safe? Now, a philosopher would answer very simple. You cannot prove the absence of something. So you can't prove it's safe. End of story. I'm going to go into a sort of a more nuanced talking about sort of the scientific and societal factors that make it so difficult to prove something is safe. I'm not going to talk a lot about expert witnesses in the court. I'll get to that at the very end. But mostly I want to talk about the context in which this scientific evidence is developed and discussed. this is bouncing around a little bit. So just before I start, just a reminder that there's if you want to ask a question during my talk, the slido.com, you can go to that, and the our event is the hash mark Destin 2021, one word. All right, so in this answering this question, then, how do you show something safe? So one very quick answer would be nothing's safe. There is no such thing as safe anything. So if you were to eat 2.5 pounds of sugar, the average human being, that would kill you if you ate it in one sitting. If you were to eat 7 ounces of salt in one sitting, that would kill you in one sitting. There's nothing that's completely safe. In fact, water, in 2007, there was a radio station in Sacramento that had a contest called Hold Your Wee for a Wee, W-I-I. If you can drink as much water, who can never drink the most water without having to go to the bathroom would win a prize, win this wee game. And a young woman actually died. She drank so much water, it killed her. It basically diluted the electrolytes in her tissues so much that her whole body shut down. So even water can kill you, which is also an essential thing, obviously. I actually learned that when I moved to Arizona, to the desert in 1999, and I live in Scottsdale, right beside the McDowell Preserve, which is a wonderful hiking area. It's just right behind my house. And one of the things you learn in Arizona is you don't know that you're sweating, but you're constantly losing water. So you've got to constantly replenish your water. And that first summer we're there, a hiker died a few hundred yards behind our house, who was an experienced hiker and actually a doctor. And the cause of death was too much water. He drank himself to death from water. And so he was out there hiking. He had a lot of water. He started to feel not well. He drank more and more, and he basically diluted the electrolytes in his tissues to such an extent that he started to lose sanity. He was apparently walking in circles for a couple hours before he expired. And so even water can kill you. So the bottom line is that there's really nothing that won't kill you. In fact, there's a headline in my presentation I have with slides that says doing nothing is bad for your health. So you can't even do nothing and it will still kill you. So you're damned if you do, damned if you don't. So, at that simple level, nothing is safe. And unfortunately, that's the way we sometimes regulate things. So the founder of toxicology in the 15th century is a guy named I can never pronounce his name, Paracelsus. And he said, all substances are poisonous if the dose is sufficiently high, and all poisons are harmless if the dose is sufficiently low. In other words, the dose makes the poison, which is often called the first rule of toxicology. And so we're going to live in this world where everything is potentially dangerous. Senator Patrick Moynihan said, life really all is about risk, and it ends badly. That we have to deal with the fact that everything is dangerous in our lives. Now, one of the problems is the way we sometimes regulate things is we regulate them based on hazard rather than risk. So this is a very important concept, the difference between hazard and risk. So hazard is the intrinsic potential of an agent to cause an adverse effect. And everything is a potential hazard. At some dose or at some level, the first rule of toxicology will tell us it can be dangerous. Risk is sort of a more advanced way of looking at it, to look at it in specific real-life scenarios. What is the actual, how does that hazard get manifested? What's the actual chances it actually occurs? And unfortunately, the way we regulate some compounds in our regulatory programs is based on hazard, not risk. A great example is a program called the International Agency for Research on Cancer, or IARC. I don't know if you've heard of that. It's an agency in France that evaluates whether something has carcinogenic or cancer potential. And over 100 countries, including the United States, automatically trigger regulatory requirements based on those IARC classifications. And they've classified a lot of things as carcinogenic, things like sunshine, things like hot beverages, things like radio frequency, which is one I'll come back to a little bit, processed meats, many, many different things. In fact, they have different categories. One is known human carcinogens, one is probable human carcinogens, one is possible human carcinogens, one is cannot determine, and then there was a category probably not a human carcinogen. There was never a category known not to be a human carcinogen. That wasn't even on the map. So you couldn't possibly know something's not a human carcinogen. And in fact, 2 years ago, they took away that category, probably not a human carcinogen. They've classified over 1,000 compounds, and only one ever landed in that category, something called caprolactam. So they don't even have that anymore. So there's no such thing as probably not a human carcinogen of all the different things people look at. And so the reality is everything can possibly cause cancer at some dose or in some way. In fact, I used to work with a toxicologist when I was in legal practice. He said, give me $1 million and I can show anything can cause cancer. And in fact, we used to do studies that are sort of out of fashion now because of this, but you could take a compound and implant it in the stomach or the lung cavity of an animal, or you could, what's called gavage dosing, of just put a huge, what's called bolus down their throat, stick it down their throat, and it gets this massive dose in their stomach, their lung, or their throat, and sure enough, you get cancer. But what was happening there is that you're basically having this very unnatural exposure where you are creating this big wad of a foreign substance inside an animal, just like in a human. You have an inflammation. And when you have inflammation, you have cell proliferation. When you have cell proliferation, you have a DNA replication. When you have DNA replication, you have mutations. And when you have mutations, you have cancer. So whenever you have inflammation, you're increasing your cancer risk. So of course you're going to get cancer if you do this very unnatural experiment, put a big wad of something inside an animal. It's not a realistic way of exposure. But that's how we did a lot of animal testing for years, and we get these results that we now realize probably aren't realistic. So that's one, answer is, yeah, everything's got a hazard or a potential hazard, and that would be the end of the story then. And so, how do we live our lives? How do we decide anything? So we got to go beyond hazard. And so it's really important to not base decisions on hazard, because everything is potentially hazardous at different concentrations for sure, but that's what we care about. We care about what is the actual risk of a real life scenario of something that we're going to encounter in our lives. So that's sort of one of the real lessons of the last 30 or 40 years of risk regulation, is that hazard-based regulation is going to steer us wrong, because anything we study is going to be hazardous at some potential level. So what is the risk? So how do we determine what is risky? So this is where we have to rely on science. When we evolved in the caves and so on, we could use our direct senses to determine if something's risky. We could see if that saber-toothed tiger is running towards us. We could hear the rocks coming down the cliff that are going to fall on top of us. We could taste water that's contaminated. We could smell meat that's rotten. We knew the things that were dangerous to us, and we could tell with our own senses. In today's world, that's no longer the case. There's radio frequency throughout this room. We can't detect that with our senses. There may be chemicals in our water that's crystal clear. We would never know that from our own taste of that. All the different types, there could be genetically modified food in our lunch today. We wouldn't be able to tell that. So we can't rely on our senses anymore to tell us what's there and what's dangerous. We instead have to rely on science. And so this requires confidence in science. And as you've seen probably lately, there's a lot of concern about our society's confidence in science, with some of the things you're hearing about coronavirus, for example. And I'll come back to that a little bit later. So we have to rely on science to tell us what's risky. We have to trust scientists to tell us what's risky. And that now starts to create a lot of the complications. So how do scientists try to answer that question of what is risky? And there's two main types that they traditionally use. And we have a whole talk coming up on this, so I don't want to go into it in too much detail. But I just want to focus on these in terms of how these techniques are unable to tell us something's safe and are unlikely to tell us something's safe. So the first way is through animal testing. And the problem is that for a lot of things out in our society, we have millions of humans get exposed to these materials, often at fairly low doses or exposures, but still millions of people. We cannot do an animal study with millions of rats or mice. If we do one with, say, 50 male and 50 female rats or mice, that's going to still cost a couple $1 million just for that study. So to do, 2 million animals is just simply infeasible. So the way we have to do these studies, the way scientists have to do these studies, instead do very, very high dose of a much smaller number of animals. And the sort of implicit assumption there is that a small dose to humans, to many humans, is equivalent to a very large dose to a small number of animals. Now, scientists aren't stupid. They understand that that's not going to always be true, but it's sort of the best we can do given the feasibility of this if we're going to rely on animal studies. So we give these animals these massive doses, and you may have heard of, these people, cartoons and so on, of, this rat who has 10,000 sodas, yeah, he gets cancer. But the reality is that's how we basically do most of our safety testing, is in animals giving these massive doses. We then have to extrapolate what that actually means for humans. And is it a straight line? Is it some kind of quadratic equation? There's now many different models to extrapolate this risk we calculate in these animal studies, a very high dose, to the type of doses we get as humans. And those models can have a huge difference in their results. There's a recent one done on aflatoxins, which found between the two most common models that were used a 40,000 different fold in the risk estimate. In one case, the risk was insignificant. The other one, it was huge. And so which model you use will make a huge difference in terms of what the risk is. Again, if you're trying to prove something that's completely safe, how can you do that if there's these two different viable models that each have some probability of being correct? You can't say this one is absolutely correct and this one is absolutely wrong. So there's some probability of a huge risk. You cannot get around that with our current knowledge and our current methodologies. So it's always going to be a possibility, if you're looking at it objectively, of some risk is there when you do an animal study. There's the Joyner versus General Electric Supreme Court case rejected that, though, rejected that we could use those animal models and said these massive doses of PCBs, that was the chemical used in that study, injected directly into the stomachs of animals is not relevant for human studies, for human people who are allegedly exposed at much less exposure levels. The court went on to say the PCBs were injected into the mouse in a highly concentrated form. The fluid which Joyner, the plaintiff, had come into contact generally had a much smaller concentration, between 0 and 500 parts per million. The studies were so dissimilar to the facts presented in this litigation that it was not an abuse of discretion for the district court to have rejected the experts' reliance on them. So sort of saying, scientists have to do what they do, maybe regulatory agencies have to do what they do, but when we get to litigation, we cannot rely on that kind of study to show that there is a risk, or a significant risk. But that's one problem with animal studies, but there's others. The way you basically do an animal study is you first do what's called a dose finding study, range finding study, where you basically look at, how does the animal react in a shorter study to different levels. And you find something called the MTD, the maximum tolerated dose. And that's where you start your study at the maximum tolerated dose, and then you may do half the MTD or a quarter or 3/4. But the MTD is almost surely going to cause some toxicity. And when you cause toxicity, you cause inflammation. When you cause inflammation, you go down this whole pathway and you get to cancer again. So these studies are almost by design set up to give the animal a dose that will cause some harm, that will cause inflammation, and will cause some kind of cancer. So you're almost always going to get a positive result, at least some of the time, just by the way we design these studies. In addition, we use different strains of mice and rats. And different strains are at very different risk of getting cancers. And so this also can be a way to manipulate the results to try to show one way or the other. You could pick a strain. The scientists could deliberately or unconsciously pick a strain that's very resilient or resistant to cancer, or one that's very susceptible to it. And that would help get your result you may be looking for, subconsciously or consciously again. And so, for example, there is a study on glyphosate. I know we have a talk coming up on that, and GMO corn, that basically picked Sprague Dawley as a species of the line of rats, which is very susceptible to getting tumors. And that was part of the reason that study ended up getting criticized, is because it wasn't really a fair test of that. But our regulatory agencies at least will often pick the most sensitive strain for the study and for which result to look at. In addition, we'll usually do both male and female rodents, and often mice and rats. And they'll pick the one of those that has the biggest response, because we want to be careful. We want to err on the side of safety is the argument, and so we pick the one that has the highest response. But that one may not be the most relevant to humans. So for example, in formaldehyde, a very commercially important chemical, they use the rat results, not the mouse results. The rat is an obligate nose breather. It can't breathe through its mouth. It only breathes through its nose. The mouse and the human do not. So likely, it's more likely that the mouse would be a better model for humans, but they use the rat, even though it's not the most likely one. They also assume that animals are representative of humans, and we know that's not the case. Depending on the analysis, rats and mice give the same results in only 60 to 75% of the time. So at least 1 in 4 times, the rat and mouse respond differently to a particular chemical. You can imagine the human even more so. And there's a number of famous cases now where we now know that human is susceptible to something like thalidomide or arsenic that the mouse and rat basically aren't. And other ones where the mouse and rat are very sensitive and the human isn't. And a famous example is saccharin. So for many years, the little pink packets had a warning that this may cause cancer. That's now finally gone away, because they realized that the reason that the male rat got cancer in its kidney from saccharin is it had a particular protein that bound to saccharin, that got stuck in the tubules of the kidney, that caused irritation, that caused DNA replication, that caused cancer. And that mechanism didn't exist in female rats, it didn't exist in male or female mouse, and it didn't exist in humans. And so finally, after many years and epidemiology studies showing no risk to humans, they finally took that cancer warning off the pink packets. But again, we don't know for most of these studies whether or not the human, the rat or animal study is going to be relevant to humans, but it's almost always going to have at least one arm of one of these studies showing something positive. So it's very, very difficult to ever do any significant number of animal studies and get a negative result. There's also just all kinds of subtle things that can affect the results of animal studies. So when I was in private practice before going to academia, I was representing Motorola to try to show that cell phones are safe. And we couldn't figure out how to do that. We spent a ton of money, but we couldn't figure out how to definitively prove they're safe. We suspected they were, we believed they were, but we couldn't prove it. And one time, a researcher at the University of Washington, who I think was a very credible researcher, reported that cell phone radio frequency was causing a double-stranded DNA breaks, which is very alarming because that, again, is creating mutations which could create cancer. And we talked to our scientists, and they said that just can't be. So we commissioned another researcher at Washington University, not University of Washington, Washington University in St. Louis to try to repeat the study. And he did the exact same protocol, read the other scientist's protocol, tried to replicate it exactly, got no DNA breaks. We said, do it again. He did it again, no DNA breaks. So we contacted the researcher at the University of Washington. And to his credit, he was puzzled by this and wanted to figure it out. And eventually what happened is that the scientists, and a great example of scientific cooperation, the Washington University scientists that we had hired went to University of Washington and replicated the study there, and lo and behold, they found DNA breaks. The two scientists then went to Washington University in St. Louis and repeated the experiment, and no DNA breaks. So something was going on there. Was it the water? Was it the housing, the environment, the air? We never did figure it out. Why do you do this one study here and you get the result and here you don't? With two scientists who are really trying to get to the bottom of it and could not figure it out. So there's all these subtle things going on in animal studies, and the bottom line is the more animal studies you do, you're going to get some positive results. And so you cannot prove something safe with doing more animal studies, because just eventually you're going to get positive hits, and then that could be argued to be real evidence of a risk. And it may be, or it may just be a false positive. But you're never going to get to the bottom of it with animal studies. So what do you use instead? So the alternative is to use human studies. Human studies are more realistic. Obviously, they're studying us. The gold standard for a human study is a randomized control trial, which we use for pharmaceuticals and medical devices, where you take two groups of people and you give one of them the exposure and the other a control, a placebo that they can't tell is not the real thing. And then neither the reviewers or the evaluators know which one got which. It's what's called double-blinded. The patients don't know, the doctors don't know. And you look to see if there's a difference. And these are the best we can do with human studies. But even with those, which cost a ton of money, an average drug costs about $2 billion to get approved, often we'll approve the drug based on a study on 3,000 people, and we'll put it out there with 20 million people, and out will pop out a totally new bad effect that no one saw in the clinical trials. So even those gold standard billion-dollar tests aren't always going to be accurate. But the problem is when we're talking about chemicals and pollutants and so on, we can't ethically do a randomized controlled trial. We can't deliberately expose people to something that we think may be dangerous. So instead, we have to rely on natural experiments of where people may have been exposed through occupational exposures or an accident or some other event that's occurred. And the problem with that is we can't control it nearly as much as we can in the randomized control study. And so all kinds of other things could be going on in those people that you're trying to compare. And who do you compare them to? And so this becomes very difficult to figure out what's going on. Now, if you know that there's something that could be contributing to the risk, you can try to control for it statistically. If you suspect smoking may be a factor, for example, you can ask the people in the study if they smoke or not, assuming you have access to them, that they're not deceased or anything. And in fact, smoking became an issue because of a very famous study in 1992 or 1981 that showed what this factor called confounding is, that other exposures can confuse your results, when it was announced that drinking coffee causes pancreatic cancer. And I don't know if any of you remember this is 1981, but it caused front page headlines across the country that you shouldn't be drinking coffee. It causes this horrible cancer that's almost untreatable, pancreatic cancer. And there's a huge drop in coffee drinking, and people try to back off it. By the way, today, coffee is seen as one of the most healthy, go ahead and take a drink, one of the most healthy things you can possibly drink. It's got all kinds of benefits for cancer and your heart and other things. How long that lasts for, who knows? In a few more years, it'll be dangerous again. But right now, it's at the top of the curve for being healthy for you. But in 1981, people were scared that this is causing pancreatic cancer. And it turned out, upon further examination, what happens is that people who drink more coffee, on average, are more likely to smoke, at least in 1981. And smoking causes pancreatic cancer. So what you're seeing with people who drink more coffee is the effect of the increased smoking causing the pancreatic cancer. If you control statistically for that, there's no increase in pancreatic cancer from just the coffee. And so that was a false alarm caused by confounding. And that was sort of an obvious confounding effect. But often we don't know what these obvious confounding effects are, because people are being exposed to all kinds of other chemicals and materials in their environment, to lifestyle factors, environmental factors, and so on, that we don't, we can't even catalog them all, never mind control for them all. And we know things have sometimes synergistic effects, that getting exposed to this and this causes more of a risk. There is a huge litigation between the tobacco and the asbestos industry for people who had both. It turned out the risk was 10 times more than the combination of them individually, that there's a synergistic effect, that both asbestos and tobacco are much worse than either alone added it. And so, how do you allocate in the legal system responsibility for that? That became a big complication. And so we know that there are these examples of other things making certain exposures worse, but there's other ones that compensate for them and make them better. For example, I used to do some work with the lead industry, and they were genuinely puzzled until it was figured out, because there was this famous scientist, Herbert Needleman, who was doing all these tests in inner city kids, showing lead in their blood caused a mental decrement that affected their brain development. And that was serious. And so the lead industry, which is out in some suburban areas, tried to replicate those studies and didn't get it. and actually accused Needleman of faking his results. And it was only a few years later that people realized that if you have a good nutrition, lead doesn't hurt you that much. But if you have bad nutrition, then it really does hurt you. And so the Needleman studies were done in these poor children who had very poor nutrition, whereas the industry studies had initially been done in wealthier neighborhoods, suburban neighborhoods that had good nutrition and didn't see the same effect. And what the lead industry did is went and tested in inner city neighborhoods again, and it did see the effect. And then, oh, now we understand what's going on. So there's all these different types of interactions that we can't possibly control for. So when we get human studies, and a lot of them, and again, the more studies you do, the more you're going to get some that come out positive. How do you know which are the true studies and which are looking at some kind of because of some different confounding factors? There's no way to really thoroughly rebut that, and to be able to say that those positive studies, even if they're the minority of studies, aren't worth considering because they could be in a certain environment or co-exposure that's actually showing a real risk. Another real big factor is genetics. So I'm in the process of writing a book I'm a geneticist by training, for the ABA on using genetics in toxic torque cases. It's fascinating. There's a ton of cases already. And it turns out that the genes that code for the enzymes, and there's about 500 of them, that metabolize things coming into our body, are the most polymorphic or most variable in our bodies. There's some genes that hardly change between any of us. If any kind of change would basically be unhealthy and be selected against. But these are actually selected for. To have more variations in these genes actually helps the population deal with new kinds of risks and concerns. So these genes are incredibly polymorphic. For example, the gene that would affect how you metabolize something called polyaromatic hydrocarbons, which sounds like a gobbledygook, but it's important because it's diesel and it's also barbecued meat. Half of us have copies of those genes that don't function. And those half of us are at risk of things, for example, of colon cancer from barbecued meats. The other half of us have a functioning copy of that and are not at risk. Why would half of us not have that gene, a functional version of that gene? Well, it's helpful for some other things. So these are selected for in our population and deliberately try to encourage variation in a population. And there's great studies showing why that's better for a population to have that variation. So what it means is when you have 500 of these genes, that some of us half have this one, half this one, or 20% and 80%, when you put 500 together, almost every single one of us in this room is completely unique and how we'll respond to things coming into our body, whether it's chemicals, drugs, foods, viruses, whatever. And so with that variation, how do you take that into account to show something safe? Again, you can show some are dangerous to some people, but to show it's safe for the population absolutely becomes impossible. So then you have a problem with that as well. You also have the problem of, and we have a whole talk on this tomorrow morning, on correlations, not causations. And this becomes a huge problem in epidemiology studies, that a lot of times there'll be association for who knows what reason. So I have to show this. There's a great book. It's actually a Harvard law student did this. And he has a website called Spurious Correlations. And now he put out a book. He has something like 1,300 or 1,500 correlations on there. But for example, margarine consumption versus a divorce rate in Maine. Probably no real thing. 98.9% correlation. He has the undergraduate enrollment at U.S. universities and injuries related to falling TVs. Maybe there's a relationship, but it's a 99.6% correlation. And then law books published versus bicyclists killed in collision with a stationary object. 93% correlations. And these aren't straight lines. These are wiggly lines, and both lines wiggle together. Like, what's going on there? If you just saw that, you say these things are related. But they're so ridiculous, there's no way they can be. So when you do these epidemiology studies, which are basically based on statistics, you're going to get all these incredible correlations that may not indicate causation. And we have a talk tomorrow that'll go into that in a lot more detail. But for purposes of refuting a risk, what you get then is that you get chance encounters of things going together, of an exposure and a risk. This will happen a certain percentage of times. And so the way scientists address this right now is they say if there's a 0.5% chance of this happening by chance, we won't count it. But if it's less than that, if it's less than 0.5, we'll say it's real. And so this is statistical significance, the term. This is, confidence intervals are used to calculate that. There's a big debate in the scientific community now about should we continue to use that, because it's just a convention. There's no rule, empirical reason that 0.05 was picked. It was just sort of picked because they had to pick something. And now there's a lot of, the American Statistical Associations have a big debate whether we should continue to use that. But that's what's used traditionally in science at 0.05%, which means 1 in 20 times you're going to get a false result by chance alone. And so, for example, you see studies published where they'll look at, and I was actually involved with one, where we were looking at these facilities and we looked at 20 different job tasks, 10 different job tasks for 20 different health effects. So that's 200 boxes. Well, 1 out of 20 by chance will be statistically significant by chance alone. So we're going to expect at least 10 statistically significant boxes just by chance alone. But some of those could be real, but they may be chance, and we have no way to really know usually. You could use that to generate a hypothesis that that's real and then test it again somewhere else. But the problem is to find another factory that has the exact same combination of exposures and environment is really impossible. So what do you do then when you have these subgroups? And there's a concern and some evidence that researchers, as I'll get to in a few minutes, deliberately choose those types of, they'll cherry pick. They'll look for ones that are positive and then say, look at this important finding I just made. And we'll get to that in a second. So this is called the subgroup analysis problem, which again makes it very hard to ever show something safe. There is a great example in Canada done in Ontario where they looked at the relationship between 223 medical conditions and 12 zodiac signs in 10 million residents. You wouldn't think that would be much statistically significant, and they found any relationship between them. They found a strong correlation between having the Leo astrology sign and a higher risk of developing gastric hemorrhage, and a high correlation between Sagittarians and a higher risk of fracture of the humerus, and reported this. And so I was talking to my class about this, and the student says, I don't understand. How could being a Leo make you have a higher risk of developing gastric hemorrhage? I said, that's the point. There is no reason to suspect that. It seems ridiculous. But the reality is you're going to get these results that are very strong by chance alone. If you look at, in this case, it was 2,676 results. So you're going to see these spurious results pop up. And again, you don't, in this case, they're spurious. Relationship between astrological sign and health thing. But if you're talking about exposure to a chemical and a health effect, you don't know if it's spurious or it's real. So you basically have no way to know for sure. This problem also comes up with the problem of clusters. So you hear a report of a certain town having a cluster of kidney cancer. Is that real or not? Never has a cluster been able to be confirmed whether it's real or not. It may be real in some cases, and it may, in others, maybe just chance. If you were to take, 50,000 lung cancers a year, take little marbles and dump them on a huge map of the United States, they don't align evenly. They're clustered. You get little groupings just by chance alone. So if you come along and you look at that, and a town reports, we've got a little cluster here of this type of cancer, how do we know if that's real or not? There's no way to test that. You can't replicate that town. That town is unique in its geography, its environment, other things it's being exposed to. And so you get these clusters being developed and people bringing lawsuits saying it's obvious that, this exposure we must have in this town, you have many exposures, but, this factory must be causing this because we have a higher than normal rate of this. But how do we know if that's real or not? It may be real. I'm not saying it's not, but we don't know if it is or not. So this is a problem with human studies as well. We have all these problems, all of which make it impossible to show that it's essentially safe for any compound or chemical or product. So we have both animal studies and and human studies. Neither of them can really answer the question. That's traditionally what we look at in science for risk. There's sort of this third category just coming along now, sometimes called in silico or toxicogenomics or Tox21, that are basically using new techniques to look at risk. And these are very promising and exciting. I actually do a lot of work in this myself. Things like artificial organs or organoids. There's a study last week of sort of these fake brains, these mini brains you can grow in tissue now. They're not really full brains, but they're sort of like neuronal tissue that function almost like a brain that you can now use to test things in brains. There's things called lab on a chip where you can basically have these little devices that are basically trying to replicate all the enzymes in a body and so on, and you can test chemicals in them. We have all these tests for molecular changes like gene expression and so on. And again, these are going to, I think, be incredibly helpful for helping us understand risk in a lot greater detail from products, but they're also going to be very difficult to prove something's not safe again. So one of the major types of research being done is what's called gene expression changes. Certain toxic chemicals will cause a change in gene expression long before there's toxicity and symptoms that you can diagnose. So this can be extremely useful to characterize a chemical, for example. We have 70,000 chemicals in our commerce. Only 2,000 have had the basic tests, because it costs millions of dollars. And so for the other 68,000, we haven't done that. You can look in $500 in a day and see how that affects gene expression. And so this is an incredibly interesting and exciting area, and EPA and other agencies are now trying to use this. But what does it mean to say that you have a change in gene expression after getting exposed to a chemical? How do we know that really means it's a danger? So for example, if someone was to flick off the lights in this room, the gene expression in all our eyes would change dramatically. That's not toxicity. That's an adaptive response that's going to go away. It doesn't harm us. And that's the case for getting exposed to anything. Our gene expression is going to change. So now there's all this data coming out showing change in gene expression from any chemical or exposure and being reported as evidence of potential response and maybe a risk. But we don't know if it's risky or not, because every single chemical or product is going to have a gene expression change if you get exposed to it. So we don't really know what this means. We just get all this new data that could be used to argue that this is potentially dangerous. So this third category of studies I think is going to help us understand a lot more about risk, but it's not going to help us prove anything is safe, I don't think. And so, and then finally, of course, even if we get a clean bill of health for some reason, that something is studied out the wazoo, and for some reason there's no bad studies, which nothing has ever happened that way, but let's say it did, we could never be sure that next year there's not another study that would show it is dangerous. And so there are things like, for example, CFCs were thought to be these inert chemicals that could never do any harm. And we had no idea they're gobbling up the ozone in the stratosphere. No one thought of that. Asbestos for many years was thought to be safe, and of course we now know it isn't. We'll hear about baby powder in a talk coming up at this conference. We've always thought that was safe, and now there's people saying it's not. So, just because it's been safe so far doesn't mean tomorrow there won't be a new study showing there's a risk. And so we can never be sure then that there's safety. And the more studies that are done, the more the risk of there being a positive result that may be either true or just chance alone, or some other factor causing that in the study. So if we study something more, we're going to get more positive studies. And so everything that's been studied to any significant degree, you have a lot of positive results. So that's why it's so hard from a scientific perspective to show something safe, but that's only half the story. That's looking in sort of intrinsically at what goes on in the scientific world of how we do these tests. But there's a whole other layer that has to be factored onto it, the human layer, the psychological, the social, the ideological, the professional and personal interests that affect how we then take that data and use it in, for example, the legal system. And those turn out to be probably even more influential. And so I want to talk a little bit about those in sort of three boxes. How does these social, psychological interests affect scientists? How do they affect the public? And then finally, how do they affect the courts? So these do affect scientists. As Professor Johnson said, scientists are people. The good thing about science is as a system, it tries to correct for that. It doesn't always do a perfect job, but it tries. But each individual scientist is an individual who has personal and professional interests, who basically wants to get a certain result, who has ideology and political beliefs. I once did an interesting little comparison. So there was 2 petitions filed on global warming that had thousands of scientists on each side. One saying it's not a big deal, one saying it's a huge problem. And right around the same time those petitions came forward, the Daubert case was litigated in the Supreme Court. And there was 2 amicus briefs. One was a very pro-plaintiff amicus brief that says, argued for, introducing and allowing all this evidence to be introduced. And they had about a whole bunch of scientists on that. And the other side was a pro-defendant amicus brief saying, leave it all out, cut it out, it's junk science. And a whole bunch of scientists on that. And specifically talking about Benedictine, which was what Daubert was about. And so there's no correlation between the risks of Benedictine and the risks of global warming. These are completely separate scientific issues. And yet quite a few scientists would sign a global warming brief and also one of these amicus briefs. And so you would think it would randomly be distributed, but it wasn't. Every single amicus brief writer signed a particular global warming one. Particularly the defense amicus brief always signed if they signed a global warming brief, it was one to say it's not a big deal. And the plaintiff's amicus always signed a global warming one that said it is a big deal. 100% separation. That's ideology. That's not science at all, because these questions are completely independent scientific questions. So you can predict someone's view on one scientific issue based on their position on another one. Now, these are not your representative every scientist, because they went forward and filed an amicus brief and signed a petition, which a lot of scientists won't do, right? But the ones who did are sort of maybe the more active on either defense or plaintiff side, clearly had an ideology that was driving their positions on other issues. So there's that ideology issue. But there's also, professional advancement, prestige, getting grants, getting publications, getting promotions, getting recognition from your peers. You don't do that by saying compound X does nothing. That does not get you headlines. What gets you headlines is compound X does something terrible. That's what encourages media coverage. So you want to get a positive result. And so what scientists will do is they'll get negative results, and it's very hard to even get those published in journals. They started a journal, I think it fizzled out, of journal negative results, just to try to get them into the literature. That when you do a study and you don't find anything, you can still get it published, because most journals won't publish it. What does that mean? It doesn't tell us anything. It does tell us something, but it doesn't, no one cared. And so you only get the positive studies reported. And certainly those are the ones that get in the good journals and the ones that get the headlines. So what does that do to the incentives of a scientist, right? It incentivizes you to go down that road of finding a positive result. So when you do those subgroups and you look at 50 of them and these are the 2 positive ones, those are the ones you're going to put out for publication, not the 48 that are negative. So this dynamic in the scientist is also very important. I, again, encountered that personally, and I hate to speak bad of the dead, but it was, I think, a pretty egregious thing. So Motorola was funding research by a guy named Ross Adey. Ross Adey was a scientist who was sort of seen as the dean or the grandfather of science of radio frequency. He had started working for the military in the Second World War on this issue, and had spent 40 years studying radio frequency, and basically found nothing. If you got really high dose and you caused a thermal effect, you found something, but everyone already knew that. So he had spent his whole career finding nothing. And he's getting old. And so Motorola funds another big study of his, and we see the initial results, and nothing happens when you treat these mice. And there was a strange study where you basically give them a real carcinogen, and you see if the radio frequency increases the cancer over the increased cancer already, because no one thought radio frequency would cause a cancer, but it could promote it. So these are called a promotion study. You hit the mice already with a potent carcinogen, you get their rate of cancer up to 60, 70%, then you see if the radio frequency gets it more. And so, I was a lawyer involved in the case. We reviewed the protocol of the study. Here's how the study is going to be done. We get the results, initial results, no effect. Then we see the manuscript going into publication, finding a statistically significant effect. And what Dr. Adey had done is, even though the protocol says we only count brain tumors, he went and included neck tumors after the fact, after he saw the results, because he then got a statistically significant result. And that's a no-no, right? You're not supposed to do that. You have to say up front what you're going to do. And that cancers were out going in. And then when he saw the results and saw there was a big difference between the sham and the RF in the neck cancers, he changed the protocol after the fact and added it in. And you can't do that. Now, he changed it. The results were that the radiofrequency reduced brain cancers. You would think Motorola liked that, but no, our theory was RF has no effect. So if in this study it reduces cancers, another one it could increase. So, and it was unscientific the way he did it. So we, told him that if you're going ahead with this publication, we won't fund your next study, which we'd already sort of negotiated. So he goes to the media and he starts to say that we're trying to shut him up. And then we get this phone call from him and he says, I'm going on 2020 next week, and unless you fund my study, I'm going to tell the world that this is dangerous. We're going, well, that's nice of you. And first of all, how is your study showing this protects against brain cancer going to be dangerous? Well, we had no idea how these shows work. And so I think it was Stone Phillips is interviewing him, their star expert. The industry's own lead scientist is now saying, he's blowing the whistle. And so they say to Dr. Adie, so you've got startling new findings that find an effect of radio frequency. And he goes, that is correct. Even for, and then Ross Adie goes, yes, even for brain cancer. And then they go off and have some other people talk about this causes brain cancer. They never once mentioned that his study found it reduced the risk of brain cancer. But it causes sensation in the media. But again, that was all done out of personal wanting to make an impact, right? He changed the results, something you're not supposed to do just because he wanted, after 40 years of frustration of seeing nothing, even though he's respected for doing these studies for 40 years and seeing nothing. We thought that was good that he'd done these studies and said what he did. But the reality is that he fudged the results because he wanted to make a splash. And then he threatened and he went on TV. And so you see this same phenomenon occurring in one area after another of these unresolved controversial risks, where certain scientists have a personal interest in the issue. Now, it could be legitimate. I mean, I'm not saying it's always illegitimate. Let's say you're studying compound X and you find these studies showing it's very dangerous to kids. You might get empowered and impassioned to do something about it, not just be a scientist, but to active doing it. But right now what we have is a situation where the scientists that are over and over and over again saying certain things are dangerous are invested in and highly involved with the same activist groups that are making that a claim. Where's the cause and effect? So, for example, the main study showing GMO foods are dangerous was by this guy, Eric Seralini in France, who's the leader of the main anti-GMO organization. Almost every study that shows brain cancer and epidemiology from radio frequencies, a guy by Leonard Hardall, who's very involved with the anti-RF groups. The main guy who's involved in the BPA being hazardous is very involved with those groups, is constantly organizing and helping events with that. So when you see the scientists align with the activist groups, again, there could be a legitimate reason that scientist is doing that, but you have to then question the legitimacy of their science because of their personal agenda. I can guarantee you none of those scientists I named will ever publish a study showing no risk. Every single study they publish always shows a risk. Even though in the fields they're studying, 95% of the studies show no risk. They never, ever find a study with no risk. And yet they are the spokespeople. They are the ones cited. They're the ones who create the controversy in the news. They're constantly cited. They give testimony at Congress. The regulatory agencies consider their work. And again, being very protective of wanting to make sure they're not letting something get through that's harmful, they tend to give it way too much credibility. And so as Jeffrey Cabot, who wrote a very good book about this, he says, if one's investment in a hypothesis is so powerful that one loses the ability to assess studies dispassionately and objectively, independent of whether results conform to one's hypothesis, it is easy to be misled. There are many points at which bias can creep into the design of experiment or its interpretation. So the bias can be conscious or unconscious. And so, again, you can have scientists, because of these interests, getting results that aren't true. And so John Ioannidis at Stanford published a study in 2005, why most published research findings are false, saying the majority of studies published are false because of these passions of the scientists to try to get them out that way. And, and now we have on top of that these predatory journals, which we may be talking about later, that these are basically paid-to-play journals. And I get several emails a week, as does almost everybody who's published anything and anything to do with science, saying that if you pay us $500, we will publish your peer-reviewed study, and we will peer-review it in 24 hours, and we'll get it out there. And these have very science-sounding names. They try to sound like real journals. They'll just change a few words. But you think it's a legitimate journal, and there isn't. There's hundreds of these. There's 250 predatory publishers, each publishing sometimes 100 journals. So there's thousands of these journals out there. And they claim they're peer-reviewed studies. And more of these non-credible studies are being published in these journals. The media doesn't understand the difference. Judges don't understand the difference. Juries don't understand the difference. And they're being promoted as valid studies. What's funny is that all kinds of people sort of game these systems. So a Harvard researcher submitted to 37 of these journals, and 17 of them accepted it, a study that he developed using a random word generator. And the title was Cuckoo for Cocoa Puffs. Its authors were Pinkerton A. LeBrain and Orson Welles. And half of these journals agreed to publish it on a day's notice. Complete gibberish. Other people submitted, it's all just obscene words. And a lot of these journals will agree to publish it if you pay the $500. They're often located, in developing in Asian countries and so on. So again, we have this total corruption of the system that some scientists are willingly publishing in. So we have a real problem in the scientific community. A couple of weeks ago, I had the opportunity to chair a session at the National Academy of Sciences on the 4th reference manual for scientific information for judges. They're in the process of creating the 4th one. And I got to chair the session on decision science, which is not in the current reference manual. But the idea is to add a new chapter to deal with some of these problems. And it was a great panel. We had Daniel Kahneman, the Nobel Prize winner, who has type 1, type 2 thinking, talking about noise, that all science generates a lot of noise. You get a lot of different studies coming out differently, and if you look at any one of them, it doesn't tell you anything. You need to look at the pattern. And he has a brand new book coming out on this, which should be fascinating. But the one I was most impressed with was a scientist, Zhou Meng from Harvard, who's a leading statistician. He talked about 7 different types of selection bias that scientists exhibit, of cherry-picking data, subgroup analysis, unprincipled handling of outliers, selection in which methodologies and tests they go forward with publication, selection and due diligence, publication bias, selection and reporting of the data. So this is an incredibly significant thing he put together that hopefully will be in the new reference manual coming out in a couple of years for judges to look at these factors. And by the way, this session was all recorded and will be put online within the next week or two. So again, there's this recognition in the scientific community of this potential for bias. The public is another whole sector where these things occur. We know the public doesn't understand science very well. We can see it in coronavirus a lot of times. With coronavirus, 16% of beer drinkers think the coronavirus came from Corona beer. This has been devastating for the Corona beer brand. You don't want that name. The Washington Post last year reported 7% of adult Americans think chocolate milk comes from brown cows. So every year the National Science Foundation does a study of public understanding of science. Last time, only 44% of the population could correctly say that electrons are smaller than atoms, true or false. 48% answered falsely that the earliest human beings at the same time as dinosaurs, true or false. Only 47% could correctly answer the question, how long does it take the Earth to go around the sun? 1 day, 1 month, or 1 year? So our public is increasingly falling behind on science. And if you look comparatively at other countries, we used to be number 1, we're now like 20th. Other countries, in terms of the public's understanding of science, is now surpassing ours. Why that's happening, there's different theories and so on, but we are in a crisis. My favorite example is when they give a study, this has been done several times, they ask whether we should ban dihydrogen monoxide, and they tell you what it does. It causes death due to accidental inhalation, severe tissue damage from prolonged exposure to solid DHMO, major component of acid rain is found in every cancer. Should you ban this? And 90% of the people say, yes, we should ban that. And of course, dihydrogen monoxide is H2O or water. These are true facts about water. And we put a chemical name on it. 90% of people, when you tell them true facts about water, would want to ban water. So we don't have a lot of confidence in our scientific community, our scientific capabilities of our public. Hate to be elitist about that, but that's a reality. And then, we have this increased focus on risk. Aaron Wildansky said several years ago, it's so extraordinary. We're the most healthy and longest lived population ever, and we're most concerned about risk. There's a German philosopher, Ulrich Beck, who published a book, The Risk Society, saying our concern about risk is now matching our concern about wealth. We are so obsessed with risk, and maybe it's because we have so much to lose now. Maybe because we are so lucky and healthy that we have the luxury of being worried about all these types of risks. But the reality is that we're very attuned and sensitive to this without a lot of scientific understanding. A lot of the things we're concerned about are these synthetic chemicals. We don't care about the natural things. So I have a box of over 100 proven examples of organic foods killing people. Now, I don't think organic foods are unsafe, but if you wanted to get rid of one dangerous food from your diet, it should be organic foods, because they have all kinds of things wrong with them. And it kills people. Documented examples. They spend millions of dollars campaigning against GMOs, which has never harmed a single person. And yet, where does the media cover? They cover the GMOs, not the organic. And so you get this sensationalism and this one-sided study analysis of these. And now we have this all exacerbated by social media, where the stuff you hear about different kinds of risks and chemicals. So be honest, I'm a GMO proponent. I get so many relatives and friends sending me articles about GMOs harming people. And it's completely bogus. You can show it's bogus, but these are spreading all over social media. There's no referee to try to bring these into control. And so this all then comes together because there becomes this concern generated by one study or by allegations that then cause media coverage, that then cause maybe a congressional hearing, that then cause regulatory agencies to look at it. And what do? They then fund more studies. And the more studies you fund of something, the more likely you're going to get a positive result. And so we get this system in place that's just generating these controversies over politically targeted examples. And so again, it's not objective, it's not scientific, it's completely taken over by these social processes that are deciding what the priorities are. And so let me just finish by talking a little bit about the courts. So you have problems now with the courts because this is all coming into courts. These scientific and social public factors all affect the jurors, but also affect the scientists, they affect the scientific data and so on. So a company is in a very difficult position to ever say something's safe. So first of all, there's data showing what's called betrayal aversion, that if you say something's safe, the jury is going to punish you if someone gets harmed. So when I was a lawyer, one of the rules was you never allow your client to say something's safe, because it can backfire on you badly in court. Secondly, we have this problem of the G to 1, which you had the reading of, that David Fagman, G to individual, David Fagman is spent a lot of work on, that basically science looks at groups, and it doesn't really tell you anything about the individual. And so how do you basically know, if the individual's at risk or not? Now, with genetics, you can now maybe do that. You can show specific causation by showing the gene changes and other genetic changes in the individual. And so there's a whole bunch of benzene cases, for example, that if benzene causes your certain type of leukemia as opposed to something else, it's a much higher chance it does a certain translocation of chromosome 5 and 7. So that becomes probative. And there's things that both plaintiffs and defense lawyers have been able to do that. But up until now, we haven't had that capability to go to the individual plaintiff and know what's really going on. So we're stuck with these much broader studies that there's always going to be some that are positive. And then, you have the problem that I'm sure other speakers at this conference are going to talk about of the expert witnesses. And so in your readings was the article on Wendell versus GlaxoSmithKline, where the court basically was deferring to the the record, the CV of the scientists. And even though the evidence did not support what they're saying. And the article talks about this phenomenon of expert witnesses becoming invested in the case, that they get paid for it, but they also then start to believe it. And we see this over and over again in litigation, that expert witnesses, even if they sometimes are great scientists, will say things in court they would never say publicly. And so, how do we deal with that problem? And I think in other parts of this conference we'll go into that in a lot more detail. But just to throw out a few ideas, this whole idea of hot tubbing, which Australia's been using, of science days, of maybe making expert reports public so people will be held accountable for them. But I just want to close by the example I love best was this. The New Mexico Senate and House passed a bill, unfortunately vetoed by the governor, said when an expert testifies during a defendant's competency hearing, they shall wear a cone-shaped hat that is not less than 2 feet tall. The surface of the hat shall be imprinted with stars and lightning bolts, and additionally they shall be required to don a white beard and shall punctuate crucial elements of their testimony by stabbing the air with a wand. And unfortunately, that did not get passed, but that would have made it clear that some of this stuff is kind of pseudoscience. But so, in the end, we're left where the philosophers started with, that you can't prove a negative, you can't prove something safe. But if you spend time going through the scientific and these social factors, I think there's just no way you can prove something is safe. Maybe there's some hope with some of these new genetic and other techniques, but we'll have to see how those play out. And with that, I've used up all my time. Sorry if you had a question, but happy to talk later. Thanks.